Hello, AP Physics students. You had a request, or one of you had a request for some explanations of the conceptual questions in the current assignment on Chapter 6, Work and Energy. So I thought I'd try to make a video addressing those questions. The first is number 4, can the normal force on an object ever do work? And explain. So I think you want to answer no, the normal force cannot do work. And in most cases, oh, I forgot to turn this light on. In most cases, that is true. Turn that light on. I'm thinking of the case where you have a horizontal surface and a box, and you're pushing that box on the surface, and the normal force on the box is straight up, right, 90 degrees to the surface. The box is sliding to the right. Normal force is up, and so there's no work. And in the case of sliding down an inclined plane, same story. The box slides down the plane, and the normal force by definition is perpendicular to the plane. Again, zero work done. So in those two cases, the work done by the normal force is definitely zero because the force exerted by that surface is perpendicular to the surface and the object is moving parallel to the surface. There is a way that the normal force can do work. Think about you preparing to jump off of the floor. So you've bent your knees, and your feet, because of that bending, are pushing down on the floor, and the floor pushes up on you. In order to get you to accelerate up into the air, in order to get you to move up into the air, the normal force on your feet, F sub n, must exceed the pull of gravity on your body. There has to be an imbalance in those two forces. Those are the only two forces acting on you as you jump. So as your legs push up and your legs straighten into the jump, the normal force pushing on your feet is larger than the weight pulling down on your body so that you can accelerate up into the air. So in this case, the normal force on your feet is in the same direction as the motion of your at least center of mass as you move up. Now there is work done. Non-zero. Positive in this case, work done by the normal force. Definitely counterintuitive for that third case. The next question, number 8, tells you that a hand exerts a constant horizontal force on a block that is free to slide on a frictionless surface, as shown in the figure. The block starts from rest at point A, and by the time it has traveled the distance d to point B, it is traveling at speed v subscript b. When the block has traveled another distance d to point C, will its speed be greater than, less than, or equal to double the velocity? So I think we could have answered this with kinematics and Newton's laws. We totally could have answered it with kinematics and Newton's laws. We would talk about the force on the block that causes it to accelerate. The acceleration is force over mass. And then we're comparing distances and velocities. And so we would think of the kinematics equation, v squared ending is starting speed squared plus 2a delta x, where we're looking at different distances, constant acceleration, and different ending speeds. I think it would be nice to talk about this in terms of work and change in energy as well, and we'll see that we get the same answer. So we know that the work done by the hand is equal to force times distance, and we know that this constant force is causing it to slide distance d and then distance d. We know that the work done by the hand causes a change in kinetic energy of the block, because the problem tells us that it's a frictionless surface and there's only this one horizontal force acting on the block. So I know that force times distance is equal to half times mass times ending velocity squared minus half mass starting velocity squared. It starts at rest at x equals 0. It goes a distance d. So at distance d, it develops speed vb. So at distance d, we've developed speed vb here, half mass velocity squared. The question is, if I double that distance, do I double vb? And the answer is no, because the distance is directly proportional not to v, but to v squared. When I double the distance, this whole quantity, v squared, doubles. So double the distance, not double v, but double vb, quantity squared. So the velocity has not doubled, but square root of 2 increased because of that velocity squared relationship. We have the same relationship if we think about Newton's second law and the velocity squared kinematics equation. Number 10. A hill has height h, a child on a sled with total mass m. So I'm assuming that means total mass of the child plus the sled. Slides down starting from rest at the top. Does the speed at the bottom depend on the angle of the hill if it's icy and there's no friction, or if there's friction and it's deep snow? So we have two questions really to answer here. We have icy, no friction versus snowy, frictiony, right? Okay, and so in all cases, we have a kid sliding down a hill. I'm not going to try to draw a kid on a sled, but total mass m, right? Kid plus sled, total mass m, hill angle theta. So we can think about this in terms of conservation of energy. We could also answer this in terms of force and kinematics, force, acceleration, and kinematics. But since we're in the work energy unit, we should think about work and energy, or in this case, really conservation of energy. So at the top of the hill, the kid is full of potential energy, full of gravitational potential energy. And starting at rest, no kinetic energy. At the bottom of the hill, the kid is going fast, and it's the kid has dropped to the bottom of the hill, so no gravitational potential energy, at least compared to its lowest point in this consideration, and full of kinetic energy. We're remembering that gravitational potential energy has to do with position above the surface of the Earth, and kinetic energy has to do with velocity. I don't know why I wrote the tilde there. It's just equal to. It's Friday afternoon, folks, and I'm making a video, and so I'm making mistakes. In any case, icy, no friction, snowy with friction. In both cases, we have a kid who is starting with gravitational potential energy and ending with kinetic energy. So if there's no friction, then the mechanical energy at the top, the gravitational potential energy at the top, gets totally transformed into the kinetic energy at the bottom with no losses. Totally transformed. So the mass times g times h, the hill height, is the only component that matters. The angle of the hill will cause the hill height to be bigger or smaller, but the angle of the hill doesn't change the fact that all of the gravitational potential energy gets transformed into kinetic energy. In the case of friction, we have to think about how the gravitational potential energy at the top gets transformed into kinetic energy, but there's friction involved in this transformation. So some of that gravitational potential energy gets sort of sidetracked into work done by friction, which causes the kid and the sled to heat up. So